In this video, we're going to learn how to identify components of schematics. But first, let's talk a little bit about what schematics are. Schematics are an abstract design of electrical circuits. So it's a representation of a real electrical circuit. And often it's super abstract. It's independent of the physical layout. It's independent of the physical characteristics of the components. It's just a logical connection. It's a way that we communicate the electrical connections between components and component requirements, such as their values and what type of components we're using. So this is a very high-level description of electric circuit. In the overall electronic design process, schematics are developed very early on. So usually first we start off with some kind of concept, some kind of application that we want to design. Then we prototype it on a breadboard, we figure things out. And as we're doing that, we're developing a schematic, a way that the pieces are connected together. And then once we have that schematic, we can formally commit it into a piece of software, right? So if we're developing a product, we want to make sure that that schematic is built in. In modern software, we can do what's called an electrical rule check to make sure everything is connected well, and it's kind of a check to see, or a sanity check to see if what we've actually built is what we want to implement, and there's no mistakes that have been made or anything like that. Once we do an electrical rule check and we pass that check, the ERC, then we can start to do a layout. We can build a printed circuit board by laying out the physical connections between the components rather than just the conceptual connections between the components. We actually lay down traces that physically connect the wires, physically connect the components on the board. Once we do a design rule check to make sure no things are overlapping and we've got no signals crossed or anything like that, we can send our design off to be manufactured and we get a real printed circuit board. Once we have that printed circuit board, we add components to it, we assemble it by soldering components to it either with surface mount or through-hole technology, and then finally we can test it to see if it actually works. So PCB layout usually starts with a schematic like this. This is a schematic for something that I actually built while I was in college. It's a Wi-Fi connected, sorry, not Wi-Fi, it's an internet connected, Ethernet connected energy monitoring system. So this is the schematic that I started with. You can see there's this is the processor for the chip, this is the Wi-Fi, actually, it's the other way around. So this is the processor for the device, and this is the Ethernet interface. And then there's all this support electronics, all of my I/O, all the power filtering, all kinds of stuff like that that I wanted to have included on the device. And then I lay that out using Eagle, which is a electronic design software, and I can get this manufactured, and then I can build it and sell it, and that's what we did. We didn't sell many of these. I sold maybe 5 of them, but it's illustrative of the process of where we go from a conceptual to a physical, the actual device. So let's look at how to identify some of the components on our schematics. Right. First off, there's 2 different kinds of components. The first is called passive, and the passive components are things like capacitors, resistors, inductors, diodes, things like that. Really simple, basic devices. And then there are active devices like integrated circuits and transistors. And the difference between active and passive devices is that passive devices just let current through. They have some basic characteristics, but they don't control current using another signal, right? So a transistor, that's exactly what a transistor does. It controls the flow of current based on another electrical signal. So that's the main difference between active and passive components. Resistors, you guys are probably familiar with these. They have these 3 symbols. There's the US symbol, which is a little squiggly line. European symbol looks like this. It's just a little box. And then this is a variable resistor. And this arrow across it is a theme that you'll see often in all of these things, all of the things that we're looking at. If it's got an arrow across it, that means it's variable. So there are such things as variable capacitors, variable inductors, all those sorts of things too. And they'll all have an arrow across their main symbol. Note that around the symbol there are 2 numbers. First is R1. This is a component identifier, and basically it's how we map from the schematic to the physical board, to the printed circuit board. Often we'll have next to the place where something needs to be soldered down, we'll have the name, the same component reference laid down next to it, so we know exactly where to put a particular value, which is this number here. This is a 10k ohm resistor, 10 kilo ohm resistor, and this value is what specifies the characteristics necessary for that particular resistor. Now notice there's some other stuff that's missing here, like the power of this resistor. This resistor isn't specified as, it could be a 1 watt resistor, it could be a quarter, an eighth, or a 16th. How much resistor we need to handle whatever current is going to be passing through it is not specified on this, and it's not often specified. So what comes with a schematic is usually what's called a BOM, a bill of materials. And this BOM gives us the specific resistor that we want to use. So as we're building a schematic, as we're building a circuit, we go through and we find suppliers that have a particular component that we want to use. We associate it with the symbol on the schematic using the reference designator, and that gives us all the information we need to recreate it later. Next is capacitors. These are very simple. They come in two flavors. There's the electrolytic capacitors, which have just the two flat plates as their symbol, and they're noted with farads. Usually it's picofarads or microfarads or nanofarads or something like that. The reference designator for capacitors always starts with a C, so that's what we see here. And then there's polarized or electrolytic capacitors. Electrolytic capacitors have a orientation, so in contrast to a ceramic capacitor or one of these basic ones, the ceramic capacitors are not aligned. So I can put them in any orientation. I can flip them around side to side, no big deal. But an electrolytic capacitor, it must go in only one way. And the symbol has that note on it. So there's a little plus, or just the flat side. The curved side is always the one that is on the negative side. And for the actual component, the long side always goes with the plus. And I always think of it as this one's got extra, so it's plus. It's the big side, it's plus sized, and it's got the extra leg. And that's the one that goes in the hole that has the plus orientation on it. And the minus side goes in the other one. All right, so that's a pretty basic for capacitors. Inductors follow a lot of the same rules. Here is the symbol for an inductor. It starts with an L. The reference designator starts with an L in this case, and we measure the value in henries, or microhenries is most commonly used in these. And there's a couple of kinds of different inductor signals. Air core inductors. Inductors are just coils of wire, right? So depending on how they are built, they're going to have different characteristics, and the symbols will reflect that. So most often we'll see these air core ones, and these are non-ferrite inductors, and they won't have any metal inside, so they'll kind of look like this. Iron core or ferrite core are more commonly used in power circuits, and they'll have some kind of iron core like this one. So there's an actual metal ring, iron ring that is the coil is wrapped around, and that's the difference between those symbols. Diodes are super common too. You'll see these a lot in power systems, and LEDs. LEDs are diodes. They're light emitting diodes. So you'll see this symbol a lot. If it's a light emitting diode, it'll have two little arrows sprouting out of this, just kind of shooting off to represent the light that is coming out of the diode. The diode symbol is also polarized. So there is a cathode end, a negative end, and there's a positive end, and it's always going towards the line here. So the idea is that a diode is a one-way valve. So the symbol itself actually represents the direction that current can flow and the way that it can't. So current can flow from positive to negative. That's why the arrow points this way. But it can't flow from negative to positive. That's why there's a wall here. So it hits the wall going this direction, and it passes through going that direction. The barrier line here also represents the line on the diode itself. And there's a couple of different kinds of diodes. You might see black plastic bodied ones. Those are usually power diodes. They can handle a lot of power. They are used in rectifier circuits and stuff like that. This is a signal diode. It's a little tiny diode with a glass body, and the black line on it represents the bar on these things. For LEDs, The bar is usually a flat side on the LED, but the negative, the shorter leg, is usually the same thing as the bar. So that's the negative side. And notice that the other one has a long side. So there's a plus side, that's the anode side. That's also the longer of the two legs, and that's how you determine which way that goes. Diodes also have, instead of a value, they have a part number, right? So this is a semiconductor device, so it's got a lot more characteristics than just a resistor or an inductor or a capacitor. Rather than just a specific value, it's going to have some very specific characteristics. So usually, instead of a physical quantity, we have a part number that's listed with it. And all the devices that follow after this are going to be having part numbers instead, because we're looking at semiconductor devices now. So transistors, for instance, have a symbol that looks like this. This is a BJT, a bipolar junction transistor, and this one in this case is an NPN because the arrow is not pointing in. That's how I remember NPN. If the arrow is pointing in, that's a PNP transistor, and again, it has a 3904. This is a part number for the transistor, not the sort of physical quantity. Transistors, weirdly enough, also have a Q as their designator instead of T. You'd think T would be it, but transformers take the T reference designator. So that's a BJT transistor. This is a MOSFET. This is, again, a different kind. It's a field effect transistor instead of a binary or bipolar junction transistor. So it's got a slightly different schematic there too. And notice that it also has a Q designator and a part number. Now, integrated circuits are probably the most complicated one because they have to capture a lot of information. They have to capture the pinout, so that's how the individual pins are connected to the body. So you'll see that basically on these devices, they have each of these legs are numbered. Right, so on the devices we've been looking at so far, we've only had 2 or 3 legs, and it's not been that big of a deal. But on these, each of the legs are numbered, and it always starts with you look at the top. The top is this little cutout on the integrated circuit. Then there is usually a little dot right here, and that indicates pin 1, and it goes 1, 2, 3, 4. 5 is over here across the body, 6, 7, 8. And all of those pins do different things. So the schematic symbol for the integrated circuit has to represent what those functions are. Now you notice that this is the pin numbers are not in order, right? So we've got ground 1, which is this pin, and 8 at this end. Those are upside down, so to speak, because they're not at the bottom. But then there's 5, 4, 2, 3, 7, 6. None of them are in order, right? So the idea here is that the schematic represents the logical layout, the most convenient layout for communication, rather than the physical layout. So these pins, you need to pay attention to the pin numbers next to these representations, because those are the physical pins, not the way it's laid out on the schematic. Right? The names next to each of the pins, those are the representation of the function of those individual pins. So these are how what each of these does. So you can see there's V+, that's where we connect the supply voltage. There's ground, there's trigger. I don't remember what the rest of these are. But there's also a pin number up here. That's, or not a pin number, a part number. That's what the device is. And integrated circuits always have a reference designator of U. So you'll see U1 somewhere around these things. There's a bunch of other miscellaneous symbols too, like this is a switch, there's a battery, this is a crystal, so it starts with X1. You'll see a lot of headers or connectors, and they take a bunch of different forms. So this is like a barrel jack, like the kind you plug into a wall adapter. There's 6-pin connectors, there's a different format of 6-pin connectors. All of these things look slightly different, but usually they have what's called a jumper designator or a connector designator that usually starts with J. So that's how you identify those things. So these are some of the most common symbols that you'll find on schematics, and you're going to need to identify lots of these things. So the quiz that follows, you're going to identify some components in some schematics and test your knowledge.